Getting into week 6 notes, this is section 3.1, and we're going to be talking about what the derivative tells us about our graphs. So one of the things we're going to be doing later in this section is using the first and second derivative of a function to decide what it looks like. So we're going to be building out functions like that from their derivatives. It's not going to be as crazy as it sounds. Because all a derivative really tells us is the way a function changes, right? So the first derivative will tell us approximately how inclined in a positive or negative direction our graph is, our function is. The second derivative will tell us the rate at which that changes. Third would do the rate of that, so forth and so on. Now, to start off with, let's consider we have a function like this. This is the function f of x. We don't really care what that function looks like. What we care about is that for a given a and b, f at a is lower than f at b, right? So a is less than b, and our function at a is less than our function at b. And this tells us something automatically, right? This tells us that a minus b is going to be less than 0. And this tells us that fa minus fb is going to be less than 0. So this thing's not 0, but it's negative. This thing's not 0, but it's negative. And together, this tells us that the change in our slope, the secant line from these points, or that goes through these 2 points, it's going to have a positive slope. That's what these are telling us. Because a minus b is negative, fa minus fb is negative. Neither are 0, so we can divide by each other, right? A negative divided by a negative is a positive, right? So that tells us that the slope of our secant line to these 2 points has to be positive. Now let's come back over to our graph. The secant line that goes through those 2 points would in fact be a positive slope, right? It has positive slope. Okay. Alternatively, for c less than b, and f of c greater than f of d, well, this tells us that c minus d is less than 0, so it's negative. But f of c minus f of d, well, that's going to be greater than 0. So the slope of the secant line that goes through these 2 points, it's going to be negative. Right? Because a positive number divided by a negative number is still negative. So the secant line that goes through these 2 points has to have negative slope. And we see that here, right? Have a negative slope. Okay. Now I wanted to start off this way because over the break, while y'all were out, I went ahead and jumped through the notes and realized some of the notation I use here is messy. Yeah, it's messy. It's not easy to read. So I want to go ahead and write it on the board.
Yeah, that doesn't look as bad on the board, but that next slide is a little.
Right, it is, isn't it? So all we're saying here is that if x is increasing and our function is increasing, well, then the slope of our function is increasing, which means our function should be increasing, right?
Yep.
Conversely, you flip that, it's going to be decreasing. It's the same thing we've got up here. Notice instead of x1, x2, I have a, b, c, d, but it's still written in the same general format. Now, what this really tells us is, imagine we let C, D get close together. Then a derivative that's positive means that your function is increasing. A derivative that's negative means your function is decreasing. And a derivative that's equal to 0 means your function is constant. So all through here, our function should be positive, and all through here, our function should be negative. Let's say this is the point 1. One, 1. And our function is x squared, my mistake, is 1 minus x squared. Okay. The derivative of our function, f of x prime, it's going to be negative 2x, right? Put in a negative value into x. Everything on the left is going to have an increasing slope. Put in a positive value, everything's going to have a decreasing slope. So let's, for example, say f prime of negative 2. This is going to be negative 2 times negative 2, or just 4. Cool, increasing. F of, alternatively, let's say 5, is going to be negative 2 times 5, or negative 10. So it's decreasing. And at 0, it is neither increasing nor decreasing. It is flat. For a split moment, our function flattens out. And that kind of makes some sense, right? Think about basketball, just a ball in general. There's that spot at the very top that you could, in theory, balance something on, right? At that spot, it would have a derivative of 0. And that's what we're saying here. What it means for f to be constant, if it's for an entire interval, then it's 0, f is constant. If it's just for a single point, then here, it means you reach the top of something, or the bottom. Make sense?
The entire interval meaning 0, 0.
The entire interval meaning, let's say we changed our function just a little bit. I can erase this, right? Okay. Let's say so we had a function that did something like this. Let's call this g of x. Wow, those were some crooked lines. Okay. In this interval, our slope is what? Our derivative, I should say, is what? Well, I should ask, is it positive, negative, or zero?
Negative.
In here? Should be positive, it's
Positive,
increasing,
yeah.
right? So g prime of x is greater than 0. Through here, however,
It's
0. G prime of x is equal to 0.
so that's the top or
That's on the interval from a to b. So whenever your derivative is 0 in an interval, that's what you get.
Okay.
And that's why they're saying it's constant, because it's just a flat line, right?
yeah,
Nothing's changing through here. Now through here,
it's
it's increasing again, right? G prime of x is greater than 0. Through here,
and then it's constant again, and then it's decreasing. But so you were saying something about the top. You've reached the top of your
yes.
zeros. I guess I was just confused about that.
Okay, so first, on an interval, when your derivative is 0, that means it's constant. Your
Okay.
function is constant for there. However, if you have a nice smooth function,
Okay. I think I understand.
okay, let's say this is our function now. This thing has a derivative of 0 at only 2 spots. Here and here. Yeah. These 2 spots are local peaks, right? Or local troughs. This is a local peak, this is a local trough. So derivative 0 tells you a few different things. If it's on an interval, that makes your function flat. If, however, it's at a point, it means your function is either at a peak or at a trough. Cool.
That makes sense.
There is one other time this can happen. And this actually follows from both of these conditions combined. We could have a derivative of 0 right here. This is the only other time. It looks like it got flat there, right?
Yeah.
Yeah.
But it also looks like it could kind of maybe be considered a min, and kind of maybe be considered a max, right?
Yeah.
Like it looks like if you were to cut this in half, it would be a max or a min, depending upon which side you look at.
So how would you label that then?
this would just be a flat spot. We'll talk more about it after a while. But I wanted to make a point that on the interval is the only time it means that it's constant. It's at a point, there's a couple different things that could be happening. And I just wanted to make that point because last semester I noticed this was a hiccup for some students where they got this in their head. And yeah, you're right, but at a point, it doesn't mean the same thing. Cool? Cool. Now, using a similar example to what I had used, x squared, we're decreasing on the interval negative infinity to 0, and we're increasing on the interval 0 to infinity. And this makes sense because the derivative of x squared is 2x. So whenever you put in a negative number, that derivative is going to be negative. And whenever you put in a positive number, that derivative is going to be positive. So that makes sense. Decreasing, increasing. Cool. So one thing this might be useful for in the business world, let's say we want to talk about the consumption of an item, right? So in this case, we're talking about Italian cheese consumed in the US per year. We don't necessarily have to look at this graph to know that our function is increasing. All we need to do is take the derivative and check that the derivative is positive, right? If the derivative is positive, then we know it's increasing. So this is a shortcut to having to actually plot it out and graph it. Now, having said that, this point I was making before about your function being 0 at a point, what's called a critical number. And what the critical numbers do is they tell you something about the behavior of your graph, how it changes. It could tell you that you go from positive to negative slope, negative to positive slope. It could tell you that your slope was flattening out and then started increasing again, or that it was flattening out and then started decreasing again. So this critical number tells you something important about the way your function behaves. And this is why I wanted to make this point about the interval thing. So a critical number written in set theory would look like this. What this says is that critical numbers are those x values such that your function at those x values is either 0 or it does not exist. Cool. Yeah. And I should have said prime, your function, the derivative of your function. So let's say I gave you a function. Is this function increasing or decreasing? And if so, where? Changes a lot, actually. This function, when we FOIL it out, is going to be x squared minus 6x plus 9 minus x cubed. So we could rewrite it as negative x cubed plus x squared minus 6x plus 9. I have no clue what this looks like. I can't plot this right off the top of my head. I know I have a few zeros that I could work with, but that doesn't look like anything to me right away. And I'm being totally honest about, like, I don't know what this graph looks like right off the top of my head. But I can take the derivative of this function. G prime of x. So the derivative of negative x cubed plus x squared minus 6x plus 9. That derivative is equal to negative 3x squared plus 2x minus 6. Okay, now we got something we can work with. Because we can set this thing equal to 0. Now, why do we want to set this equal to 0? First, let me ask, is this function defined everywhere? It's a polynomial, so yeah, right? So that means we only need to start ourselves with critical numbers that are equal to 0. Now, why is that? What does this critical number tell you? It's going to tell you when you have a peak or some change, or a peak, a trough, some fundamental change in your function, right? It's going to tell you when your function might be changing from positive to negative slope. Does that make sense what I mean? If you have a peak or a trough, then what necessarily happens is that you go from increasing to decreasing or decreasing to increasing, right? Makes sense? The only other case you might have is that you flatten out for a little bit and then you go back to what you were doing. So this is a natural point to check what your function's doing. Does that make sense what I mean? Yeah? Okay. Let's set this thing equal to 0. All right. Now what?
We subtract it, or add a 6.
Nope, we have to use something from algebra. You want to know when a polynomial is equal to 0, what is it we're going to use? Got it here. Come on, y'all know this. Everybody's favorite, most useless thing in the world to complain about. It's actually not useless at all, it's super useful. But everybody likes to complain that it's useless. Folks at home can't see this, so let me go back to Zoom really quick. Share screen, desktop. We're to apply the quadratic formula, right? Agreed? We're setting our polynomial equal to 0, and we want to know what x is equal to. So we have to apply the quadratic formula here. So a is equal to -3, b is equal to 2, c is equal to -6. That means x here is going to be equal to -b plus or minus the square root of b squared minus 4ac. 4, -3, -6, all divided by 2, -a, or I mean 2a, so -3, right? Yeah. This is in your textbook too, so if you have the digital copy or the physical copy, you don't remember the quadratic formula, pull it up on the back of the book. That's why I pulled this out the way I did, because I wanted to show that you do have your resources as well. You do have your books at home. So this is going to come out to be -2 plus or minus the square root of 4 minus 76.
No, 72.
Yes,
Sorry,
not a problem.
I thought it ended up being probably.
I mean, you had it. It was just that 6 got stuck in your head, right? That's something that we all do, like, honestly. All right, so this is going to be a number that I don't know right off the top of my head. -2 plus or minus the square root of
60.
Does it not have any zeros? It should. I thought it did. Okay, -68 divided by 6. That's 18. 72. Okay, it doesn't have any zeros. Cool. Let me check this on the calculator. Because I may have just picked a really bad function. -3x squared plus 2x minus 6. No, it doesn't have any zeros. Cool. Okay. So, our function doesn't have any zeros. What does that tell us?
It's
What is that? Our derivative doesn't have any zeros. What does that tell us about our original function? Look what's happening here.
reflected over like that.
All of our derivatives are negative, right? Yeah, so they're all decreasing. So what does that tell you about this function? It's going to be decreasing everywhere, right? So let's plot that really quick. New function, negative x cubed plus x squared minus 6x plus 9. What do you know? This function is in fact decreasing everywhere. Our function, this one over here, just like this, right? This is g of x. And the derivative did something like this. This was g prime of x. So g prime of x being negative everywhere gave us some good information about g of x, right? It's always decreasing. Awesome, that would be convenient potentially if what we're trying to find is how to graph this thing and we don't have a clue of what it looks like, right? Now we automatically know it's going to be negative everywhere. And since it's a cubic, we already have an idea that it's going to be this way, right? So 2 points that might be useful to know then would be when x is equal to 0 and when the cubic is equal to 0. Because that gives you this point and this point. Then you can plot the rest of it, right? Make sense what I mean?
Yeah. So,
Go ahead.
it's,
So the point here is that knowing something about these derivatives tells you something about these functions. And that's good. That's useful. Does that make sense to everyone? Folks at home, does that make sense?
Yep.
Yep, awesome. Now, what I was trying to do was actually show how to use this entire thing. Unfortunately, I just picked a really bad function. What you want to do is you want to look at your function first. Take the derivative of it. Set that derivative to 0 and check when it's also undefined. Then you're going to take all of those x values and check on either side of them what your derivative is doing. If your derivative is negative, then you know your function is going to be decreasing. Here, we had no zeros in our derivative. So all we needed to do was check 1 point on our function to say, okay, our function is decreasing everywhere. And we knew something automatically about the behavior of our function. Make sense? Okay, they use a better function than I did. Much better function. All right, our function here is x cubed minus 3/2 x squared. We can't simplify this any further. So let's go take the derivative of it. X cubed minus 3/2 x squared. Well, this is going to be 3x squared minus 3/2 2x, which is equal to 3x squared minus 3x. We can factor out a 3x here, can't we? So let's go ahead and do that. 3x is equal to x minus 1. Okay. This thing is equal to 0 at 2 spots, right? When x is equal to 0 and when x is equal to 1. Yeah? So, g prime of x equal to 0 implies x is equal to 0, or x is equal to 1. Now we've got our critical numbers, because our polynomial is continuous everywhere. So we don't need to worry about any place where it doesn't exist or is undefined or whatever, right? We just need to worry about the zeros. Cool. Let's draw out a number line. X is equal to 0. X is equal to 1. Now let's pick a number less than 0. Let's say -1. Well, this is the interval -infinity to 0. This is the interval 0 to 1. This is the interval 1 to infinity. Let's choose f of x, or let's choose x equal to, like I said, -1. Okay. When we plug in -1 here, we're going to have we're plugging -1 here, we're going to have 3 times -1 times -1 minus 1. So that's going to be -3 times -2, or -6, right? Now on the interval 0 to 1, let's pick 1/2. Seems like a decent number, right? Actually, let's pick 1/3 because it'll cancel out that. Cool. So x is equal to 1/3. 3 times 1/3 times 1/3 minus 1. So that's going to be 1 times -2/3. So this is going to be -2/3. Now let's pick a number in this interval. Here I would say let's pick let's pick 2. Three times 2 times 2 minus 1. So this is going to be 6 times 1 is 6. All right, what we just found, coming over here. Let's mark our intervals. X is equal to 0. Our critical points, I mean. This is our other critical point. X is equal to 2, right? I mean, x is equal to 1. What this tells us is that in the interval from -infinity to 0, our function is negative, so it's decreasing. In the interval 0 to 1, our function is again negative, so it's decreasing. And in the interval 1 to infinity, our function is increasing. Now let's go ahead and graph this function. X cubed minus, what was it, 3/2 x squared. So check it out. Our function, I did something wrong. What did I do wrong?
Is it the -6?
Yes,
Okay,
it's the
I was
negative
wondering,
6.
that was throwing me off.
That was a typo on my part. This should be 6, right?
Yeah.
Okay. So check out what we've got though. Our function up until 0 is increasing. After 0, it's decreasing. And at 1, it starts to increase again. We're increasing, decreasing, increasing, just like what our critical numbers insinuated. So we're starting to pick up on this insinuation from our derivatives about what our function is going to look like, right? This is showing us that there is some relationship between the process of graphing our function and checking how these derivatives behave. Does that make sense? So if we wanted to actually have plotted this based on this, let's say we don't know what that looks like. We go back to that. Let's throw in 0 into our function. G at 0 is equal to 0 minus 0, so 0. Cool. G at 1 is equal to 1 minus 3 over 2. That's going to be equal to negative 1/2, right? So our function comes at 0, 0 this way. It comes at the point one 1/2 minus say 1 negative 1/2 this way. Right? So now you say, all right, that's a cubic. So I know it's pretty smooth. I know it's going to look something like that. Which is exactly what the graph was. Does this make sense to everyone? Yeah. So this section is entirely about figuring out what a graph looks like just based off of its derivatives. And this process is going to be long, because we're not going to just work with first derivatives, we are going to have second, third, and fourth. And I'll talk more about that in a little bit. But for right now, jumping to the solution and comparing the book's answers to ours, again, we did find that it was in fact increasing up to 0, right? Decreasing between 0 and 1, and increasing from 1 to infinity, right? The way they go about checking these, they did much like I did, broke up intervals based on your critical numbers, which we said were 0 and 1, right? And they said, all right, your interval from negative infinity to 0, your interval from 0 to 1, your interval from 1 to infinity. Let's check in this first interval, negative 1. Let's check in this second interval, 1/2. Let's check in this third interval, 2. Well, at negative 1, your function comes out to be 6. So in that interval, your function is increasing because 6 is greater than 1, right? Okay. In the second interval, it's decreasing because your function comes out to be -3 over your derivative evaluates out to be -3/4. And then again, in the next interval, it's increasing. Now we could have more complex examples like this down here. This is the function x squared minus 4 raised to the 2/3. This thing should have a critical number at -2, at 0, and at 2. We can see at 2 it would, right? Because if you put in -2 or 2, this whole thing is going to become 0. Well, by chain rule, we should expect this thing to last, right? Since this is going to be u. Lo and behold, it does in fact last after we take the derivative. Now we're going to look for when it's undefined. Since this thing can either be 0 or undefined, it's going to be 0 when x is equal to 0, thanks to that denominator, right? And to the numerator. And thanks to that denominator, we get undefined at 2 or -2. Does everybody follow me? So we have critical numbers then at 0, -2, and 2. So we're going to break up our intervals into 4 intervals. Notice you're always going to have one more interval than you do critical numbers. What we want to do is check if our derivative is positive or negative in here, if it's positive or negative in here, positive and negative in here, and positive or negative in here. So, checking, we've got our interval from -infinity to -2. Let's throw in -3. Our function comes out to be negative, so it's our derivative comes out to be negative. So our function is decreasing. In the interval from -2 to 0, let's throw in x is equal to -1. Our derivative at -1 is greater than 0, so our function must be increasing here. In the interval from 0 to 2, x is equal to 1, or let's use x equal to 1. Our derivative at 1 is less than 0, so our function must be decreasing in that interval. And finally, in the last interval from 2 to infinity, let's use x is equal to 3. Our derivative then is going to be greater than 0, so our function must be increasing. So decreasing, increasing, decreasing, increasing. Comparing it to the actual function, decreasing, increasing, decreasing, increasing. Now notice here, just knowing this isn't quite going to be enough to get you to where you want to be if you want to plot this graph, right? Unless you really know how these things behave, just knowing where you're increasing, decreasing, increasing, decreasing at, that's not going to be enough anymore for these types of functions. Luckily, there are other derivative methods that we can use to get us over that hurdle. So, as another quick example of like what we saw with that first example, that it was always decreasing, we could have an example like this cubic here, x cubed minus 3x squared plus 3x. The derivative of this thing, when we factor out 3, we find that this thing comes out to be 3 times x minus 1, that quantity squared. So that means we're only going to have a 0 in our derivative when x is equal to 1. because that's what this is. This is the derivative of our original function. Set that thing equal to 0, because all polynomials are continuous everywhere. So we don't have to check for undefined values, just zeros. We factor it out. We see immediately that our only 0 is when x is equal to 1. So we only need to check the interval negative infinity to 1 and 1 to infinity. So let's check at 0 and let's check at 2. At 0, the derivative of our function is positive, so our function is increasing. And at 2, the derivative of our function is positive, so our function is increasing. So what we've got is our function is increasing, 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 flattening out, flattening out, flattening out, flattening out. Increasing, 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 increasing. That's what's happening here. Excuse me. Throat's getting dry now. I'm talking too much. So I'm going to go ahead and jump over this just so we can get into section 3.2. All of the problems that I jump over in class, check them out at home. They do help. They help give context. So we now have an idea of what's called a relative extrema. Before I define what a relative extrema is, what do you think a relative extrema is, just based on its definition? Like, I mean, not on its definition, on its name.
Relative extreme.
Yeah, what does that mean then?
Something that you don't see very often.
I want to say it like that. Think about this picture. If you had to say this picture had, or this graph had any relative extremes, where would you call
Like a max point,
them? Okay.
that's what I would call it, just a max amount or a max point somewhere on the graph.
Okay. Or a minimum, right? Because you could have the negative extrema too, which in the negative sense, it would be a trough, not really a negative, right? So it would be a max or a min. And when we say relative, what we're talking about is compared to all the values immediately around it, all the x values immediately around it. So here, if we consider a small window of x values, we see we have two relative extremas, right? We've got what looks like a max and what looks like a min. And that's what these things are. Is a relative extrema is a point which, if you jiggle your x value about that, then you're no longer a max or a min. In other words, pick a c value, x is equal to c, jiggle that x value. If everything other than that c is below f of c, you're at a max. And if everything around that c is above it, then you're at a relative min. Does that make sense what I mean? So come down here, jiggle your x, and every value you're going to get is greater than at this minimum point. Singularly, everything here is going to be below everything but this maximum point. Cool? So here, we've got a C value, jiggle your X values about it. All of those X values you're gonna get from jiggling it are gonna be greater than this F of C, right? So F of whatever that jiggle is, it's going to be larger than F of C. Hence, F of C must be a minimum. Similarly, we have a maximum. If you jiggle about that, everything is going to be below it. And that's how we can detect a max or a min. Cool? So when this happens, our derivatives are going to have one or two things happening. They're either going to be 0, or they're going to be undefined. Now let's look here and see why. Our derivative is positive, 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 but it's decreasing, right? It's positive, but it's decreasing in value. We get to a point and we start having negative derivatives. So we have to go through 0 then, right? Our derivative necessarily has to go through 0. Just because it was a positive number, that positive number, the derivative of our function, started decreasing, 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 decreasing. Something happens, goes to 0, or something happens, it's negative, 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 right? So it has to go through 0 whenever we're at a max or a min, or it has to be undefined. Cool? Yeah. When it's undefined, you have a sudden jump. This is a cusp, right? And all we're saying here is the derivative from the left and the derivative from the right don't agree. Because they don't agree, you don't have a derivative right here. And since you don't have a derivative right here, we say that the derivative at C is undefined. Okay, this only happens when there's some sort of discontinuity or a cusp. Cool, all right, so we got a cusp. So as a check for relative max, or as a check for relative extremis, set your derivative equal to 0. These are your critical numbers, right? Or to an undefined value. So again, your critical values tell you about relative extremes. That said, just because it's a relative extrema doesn't necessitate that it is, let me say that again, let me say it the right way. Just because C is a critical number doesn't mean you have a relative extrema, right? We've already seen that example. Of something like this. The derivative of our function here is 0, but it's not a relative extreme. So just because you have a critical number doesn't mean that critical number is a relative extremum. But every relative extremum will be associated with a critical number. Cool. So we need to do some checking. And the way we check it is simply to say, all right, what's our relative extreme, or I mean our critical number? If we go from increasing to increasing, well, we just flattened out that this can't be a relative extremum because a relative extremum requires a change in the direction of the slope. Does that make sense what I mean?
Yeah, because that's what makes it an extreme.
Exactly, exactly. So when checking for relative extremums, you've got to check for this change in direction, as well as whether it's a critical number.
So you would describe that as a drastic change. A relative extreme would be a drastic change in slope.
I wouldn't say that it's a drastic change in slope. I would say that it's a change in sign, a change in sign of the slope, right? So x is equal to c. This is the interval negative infinity to c. This is c to infinity and beyond. If we do something like this, if we see that there's a change in our sign in this way, so we go from negative to positive, then what we're saying is our slope is this number, right? So if we go from a negative slope to a positive slope. My mistake, I wrote that backwards. Sorry about that. If as I have it drawn here, we do this. This tells us that our critical number C, right here, this thing has to be a relative min. Everything left of C is positive. My mistake, everything left of C is negative, everything right is positive. Left is negative, we're decreasing right, right is positive, we're increasing. If, however, we flip that, then we should expect our function to also flip, right? Now, here our function is increasing and then decreasing. So we should expect something like that. That's what these rules are telling us. I highly suggest you draw out all three cases just to verify them to yourself. It will make this process a lot easier if you do that. Just so you can see what's actually being said and happening. And try to draw out some of these things as we go through the next few sections, just because drawing it is going to help. Like it is going to make some of the pictures click and some of the math kind of catch. Does that make sense? Cool. Having said that, just a few more examples of what I was just drawing on the board. We go from negative to positive. So our derivative goes from negative to positive. We found we have a critical number at C. We choose a value left of it that's negative. We choose a value right of it that's positive. Our derivative is negative. Our derivative is positive, I should say. Then that critical number must correspond to a relative min. Conversely, if we choose a value to the left of C and our derivative is positive, then we choose a value to the right of C and our derivative is negative, then that critical number has to associate with a relative max. And if there is no change, it's not a max or a min. Cool? It's called an inflection point in that case. Having said that, I will let y'all go. I'll stick around if y'all have any other questions. Not a problem.
Thank you.
Did you have other questions about the homework?
No, that was the only one.
How about you? Did you have any questions?
I'm
about the
good,
homework?
yeah, no, I'm good, thank you.
Not a
I'm just
problem.
tired of you asking
I
questions.
know.
I feel y'all.
Thank you.
Y'all too. Have a good one, everyone.